Welcome. Today, we dive deep into the backbone of the internal combustion engine, the crankshaft. Imagine a car accelerating down the highway. Inside the engine, pistons are firing up and down thousands of times per minute. But how does this linear, up and down motion turn into the rotational force that spins your wheels? The answer lies in this masterpiece of engineering. Without the crankshaft, modern transportation as we know it simply wouldn't exist. Let's explore the secrets of this steel giant. A crankshaft is not just a solid piece of metal. It is a highly precision-engineered component with several key parts. First, we have the main journals. These are the central axis points where the shaft sits in the engine block. Then, there are the crank pins, also known as connecting rod journals. These are offset from the center, and this offset is what creates the crank motion. To keep everything smooth, we use counterweights. These balance the weight of the pistons and rods, preventing the engine from shaking itself apart at high speeds. Think of a cyclist. Your legs are the pistons, your knees are the connecting rods, and the pedal arm is the crankshaft. When the fuel ignites, it pushes the piston down with immense force. This force travels through the connecting rod to the crank pin. Because the pin is offset from the center, it forces the shaft to rotate. This is where torque is born. Every revolution of the crankshaft is a perfectly timed dance of physics, converting raw heat energy into mechanical rotation. Not all crankshafts are created equal. In a standard economy car, you'll likely find a cast iron crankshaft. They are cost-effective and durable enough for daily driving. However, in high-performance racing or heavy-duty diesel engines, we use forged steel. Forging involves heating the metal and hammering it into shape, which aligns the grain structure of the steel for maximum strength. For the most extreme applications, engineers use billet crankshafts, which are CNC machined from a single, solid block of high-grade steel. This ensures zero defects and ultimate reliability. Balance is everything. An unbalanced crankshaft rotating at 8,000 revolutions per minute would feel like a jackhammer. There are two types of balancing, static and dynamic. Engineers use precision machines to remove tiny amounts of metal, often by drilling small holes into the counterweights, until the shaft is perfectly centered. Additionally, many engines use a harmonic damper on the front of the crankshaft. This device absorbs torsional vibrations, which are microscopic twists in the metal that occur every time a cylinder fires. The design of the crankshaft also defines the soul and sound of an engine. In the world of V8s, there are two main types. The crossplane crankshaft is common in American muscle cars. It provides a smooth ride and that iconic, deep rumble. On the other hand, European supercars often use a flat-plane crankshaft. It's lighter and allows the engine to rev much higher, creating a high-pitched, screaming exhaust note similar to a Formula One car. It's the same engine configuration, but a completely different crankshaft geometry. The most surprising fact about a crankshaft? In a running engine, it never actually touches the metal bearings. A thin film of pressurized oil, thinner than a human hair, keeps the shaft floating. This is called hydrodynamic lubrication. Oil is pumped through tiny galleries inside the crankshaft to reach the journals. If this oil film fails, the friction generates enough heat to melt the metal in seconds, a catastrophic failure known as spun bearings. The crankshaft is a bridge between fire and motion. It endures thousands of explosions every minute, handling massive amounts of stress to keep us moving. Next time you hear an engine roar, remember the rotating steel heart that makes it all possible. Thank you for watching this deep dive into engine mechanics. Don't forget to like and subscribe for more engineering insights. See you in the next one.